You think you know our solar system, you've seen the textbook diagrams, 8 planets neatly arranged in a row, the sun at the center, maybe an asteroid belt floating somewhere in between. But what if I told you that everything you've been shown is a lie, not in terms of what exists, but in terms of scale? The distances involved are so vast, so incomprehensibly enormous, that if you tried to build an accurate scale model with Earth the size of a marble, you'd need a space larger than several football fields just to fit the sun and planets. Today, we're going on a journey to discover the true size of our cosmic neighborhood, and I promise you, by the end of this video, you'll never look at our solar system the same way again. If you're ready to have your mind blown by the true scale of our cosmic home, make sure to subscribe to this channel and give a thumbs up. Here's something I've been wondering. If you could instantly travel to any location in our solar system right now, where would you go and what's the first thing you'd want to see up close? Let me know in the comments down below. I will pin the most creative answer. Now let's begin. Let's start with something familiar and work our way outward. Earth, our home, measures about 12,742 kilometers in diameter. That's roughly the distance from New York to Tokyo and back again. It feels massive when you're standing on it, trying to walk even a few kilometers. But in cosmic terms, Earth is a speck. To understand our solar system's size, we need to grasp not just how big the objects are, but how much empty space lies between them. And trust me, there's a lot of emptiness out there. The Sun dominates our solar system, containing 99.86% of all the mass. Its diameter stretches 1.39 million kilometers, about 109 times wider than Earth. If Earth were a grain of sand, the Sun would be roughly the size of a large beach ball. But size isn't what makes the Sun remarkable in our discussion of scale. What matters is distance. The Sun sits on average about 150 million kilometers from Earth. We call this distance one astronomical unit, or AU, and it's the measuring stick we use for everything else in our solar system. Light, traveling at roughly 299,792 kilometers per second, the fastest speed possible in our universe, takes about 8 minutes and 20 seconds to cover 1 AU. Think about that. When you look at the Sun, you're not seeing it as it is now, but as it was over 8 minutes ago. If the Sun suddenly vanished, we wouldn't know for over 8 minutes. This delay isn't some quirk of perception, it's a fundamental feature of our universe where even light needs time to traverse the cosmic distances. Now let's venture outward. Mercury, the closest planet to the Sun, orbits at about 0.39 AU, or roughly 58 million kilometers from our star. The Messenger spacecraft, which orbited Mercury from 2011 to 2015, took about 6.5 years to get there, not because it traveled slowly, but because orbital mechanics required it to take a complex path, looping around Earth and Venus multiple times to slow down enough to be captured by Mercury's weak gravity. Direct routes in space are rarely the fastest or most efficient. Venus, Earth's hellish twin, orbits at 0.72 AU, about 108 million kilometers from the Sun. The Soviet Venera program and NASA's Magellan mission revealed a world of crushing atmospheric pressure and temperatures hot enough to melt lead. But what strikes me most isn't Venus's hostile conditions, it's how we measured its distance. Scientists bounced radar signals off Venus and timed how long they took to return, using the speed of light as a cosmic yardstick. The precision of these measurements is staggering, accurate to within a few kilometers across distances of hundreds of millions of kilometers. Mars, the red planet that haunts our imagination, orbits at about 1.52 AU, or roughly 228 million kilometers from the Sun. The distance between Earth and Mars constantly changes as both worlds orbit the Sun. At closest approach, called opposition, Mars comes within about 55 million kilometers. At the farthest, when Mars is on the opposite side of the Sun, the distance swells to about 400 million kilometers. This variation dramatically affects our ability to send missions there. Launch windows to Mars open only about every 26 months when the planets align favorably. The Mars rovers, Spirit, Opportunity, Curiosity, and Perseverance took between 6 and 9 months to reach Mars, traveling when Earth and Mars were relatively close. These missions revealed a world that once had flowing water, a thicker atmosphere, and possibly conditions suitable for life. But they also revealed the challenge of distance. Radio signals from Mars rovers take between 4 and 24 minutes to reach Earth, depending on where both planets are in their orbits. This communication delay means rover drivers can't operate them in real time like a video game. They must plan each day's activities, upload commands, and wait to see what happens. Now we reach the Asteroid Belt, a region between Mars and Jupiter where millions of rocky remnants from the solar system's formation orbit. Contrary to science fiction depictions showing dense fields of tumbling rocks, the asteroid belt is mostly empty space. The asteroids are spread across a region extending from about 2.2 to 3.2 AU from the Sun, roughly 330 to 480 million kilometers. If you were standing on one asteroid, you likely couldn't see the next one with your naked eye. The total mass of all asteroids combined is less than 5% of the Moon's mass. The Dawn spacecraft, launched in 2007, visited 2 of the largest asteroids, Vesta and Ceres, revealing worlds with their own geology, craters, and mysteries. Ceres, the largest object in the asteroid belt, is about 946 kilometers across, with bright spots that turned out to be salt deposits, possibly from a subsurface ocean. These missions showed us that the asteroid belt isn't just debris. It's a museum of our solar system's early history, preserving rocks that never coalesced into a planet due to Jupiter's overwhelming gravitational influence. Speaking of cosmic scales and boundaries, if you're fascinated by how far things extend and what lies at the edges of observable space, you'll love my video, What's on the Other Side of the Universe, where we explore the ultimate cosmic horizons and what might exist beyond everything we can see. The link is in the description below and on the card above. Now let's continue our journey outward through our solar system. Jupiter marks a dramatic shift in scale. This gas giant orbits at about 5.2 AU, roughly 778 million kilometers from the Sun. Jupiter is so massive that it contains more than twice the mass of all other planets combined. Its diameter spans 139,820 kilometers, 11 times wider than Earth. Over 79 Earths could fit across Jupiter's face. But here's what truly boggles the mind. Jupiter is so far from the Sun that sunlight takes about 43 minutes to reach it. The Galileo spacecraft, which orbited Jupiter from 1995 to 2003, took 6 years to get there, and the more recent Juno mission, arriving in 2016, took 5 years. When scientists send commands to Juno, those radio signals take about 48 minutes to make the round trip. Imagine trying to troubleshoot a problem when every question and answer is separated by nearly an hour. This communication delay fundamentally changes how we operate spacecraft in the outer solar system. Jupiter's moons form a miniature solar system. The 4 Galilean moons, Io, Europa, Ganymede, and Callisto, were discovered by Galileo in 1610, proving that not everything orbits Earth and revolutionizing our understanding of the cosmos. Europa, slightly smaller than our moon, likely harbors a global ocean beneath its icy crust containing more water than all of Earth's oceans combined. The upcoming Europa Clipper mission, launching in 2024, will make dozens of close flybys to investigate whether this hidden ocean might harbor life. Saturn, the ringed jewel of our solar system, orbits at 9.5 AU, about 1.4 billion kilometers from the Sun. Light takes 1 hour and 20 minutes to travel from the Sun to Saturn. The Cassini spacecraft, which orbited Saturn from 2004 to 2017, took nearly 7 years to reach this distant world. Cassini's mission revealed Saturn's rings in unprecedented detail. Thousands of individual ringlets made of ice particles ranging from dust grains to house-sized chunks, all orbiting in intricate patterns influenced by dozens of moons. Saturn's largest moon, Titan, is bigger than Mercury and possesses a thick atmosphere, the only moon in our solar system with substantial air. Cassini's Huygens probe descended through Titan's haze in 2005, revealing a world with lakes and rivers of liquid methane, rain showers of hydrocarbons, and a landscape eerily similar to Earth, despite being at temperatures of -179 degrees Celsius. Titan reminds us that Earth-like can manifest in profoundly alien ways. Here's where our journey takes us into truly remote territory. Uranus orbits at 19.2 AU, about 2.9 billion kilometers from the Sun. Sunlight takes 2 hours and 40 minutes to reach this ice giant. Voyager 2 remains the only spacecraft to visit Uranus, flying past in 1986 after a journey of 8.5 years. That brief encounter, just a few hours of close observation, revealed a world tipped on its side, rotating at a 98-degree angle to its orbit, possibly due to a collision with an Earth-sized object billions of years ago. Uranus appears as a pale blue-green disk with faint cloud features and a system of thin, dark rings. Its 27 known moons include Miranda, whose surface shows a bizarre patchwork of terrains suggesting a violent past. At Uranus's distance, the Sun appears as just a bright star, providing only 1/400th the sunlight we receive on Earth. Solar panels become impractical this far out, forcing spacecraft to rely on nuclear power, radioactive decay providing the heat and electricity needed to survive. Neptune, the outermost major planet, orbits at 30 AU, about 4.5 billion kilometers from the Sun. Light takes 4 hours and 10 minutes to travel from the Sun to Neptune. Voyager 2 visited in 1989 after 12 years of flight, revealing the most dynamic atmosphere of any giant planet, with wind speeds reaching 2,100 kilometers per hour, the fastest in the solar system. Neptune's deep blue color comes from methane in its atmosphere, absorbing red light. Neptune's largest moon, Triton, is one of the strangest worlds we've discovered. It orbits backward, retrograde, suggesting it was captured from the Kuiper Belt. Triton's surface, at -235 degrees Celsius, is among the coldest measured in our solar system. Yet Voyager 2 spotted nitrogen geysers erupting from beneath the ice, proving that geological activity can persist even in these frozen wastes. Triton slowly spirals inward toward Neptune, doomed to be torn apart by tidal forces in perhaps 1 billion years. At 30 AU, we've traveled 30 times farther from the Sun than Earth, 4.5 billion kilometers. But we're not even close to the solar system's edge. In fact, we've barely begun. The region beyond Neptune contains the Kuiper Belt, a disk of icy bodies extending from about 30 to 50 AU. This is where we find Pluto, which orbits at an average distance of 39.5 AU, or about 5.9 billion kilometers from the Sun. Pluto, famously reclassified from planet to dwarf planet in 2006, captivated the world when New Horizons flew past in 2015 after a 9.5-year journey. The images revealed a geologically active world with nitrogen ice glaciers, water ice mountains reaching 3,500 meters high, and a heart-shaped plane called Tombor Regio. At Pluto's distance, the Sun appears as merely a bright star, and temperatures plunge to -223 degrees Celsius. Yet this frozen world shows evidence of recent geological activity within the last 100 million years, possibly ongoing, challenging our assumptions about what drives planetary evolution. The Kuiper Belt contains hundreds of thousands of icy objects, remnants from the solar system's formation 4.6 billion years ago. These pristine fossils preserve the original composition of the solar nebula. Eris, Makemake, and Haumea are among the larger dwarf planets discovered there. Arakoth, a contact binary object visited by New Horizons in 2019, showed us what happens when two objects gently merge, a snowman-shaped world 69 AU from the Sun, or about 10.3 billion kilometers, where it takes over 6 hours for sunlight to arrive. But the Kuiper Belt isn't the edge. Beyond it lies the scattered disk, where objects follow highly elliptical orbits, venturing far beyond the Kuiper Belt's main concentration. Some scattered disk objects approach the Sun closer than Neptune, then swing outward to distances exceeding 100 AU. These eccentric orbits result from gravitational encounters with Neptune during the solar system's early, chaotic period when the giant planets migrated to their current positions. Now we enter truly mysterious territory. The hypothetical Oort Cloud, never directly observed but inferred from comets' behavior, is thought to begin around 2000 AU, roughly 300 billion kilometers from the Sun, and extend to perhaps 100,000 AU or even 200,000 AU. At these distances, we measure in light days and light months rather than light minutes. The Oort Cloud's inner edge lies about 1/3 of a light year from the Sun, while its outer edge might reach halfway to the nearest star. Think about that scale. The Oort Cloud is so vast that it takes sunlight months to reach its outer edges. It's a spherical shell surrounding our entire solar system, containing perhaps trillions of icy bodies, the remnants of planetary formation scattered outward by gravitational interactions with the giant planets. These objects orbit so slowly that a single trip around the Sun might take millions of years. When gravitational perturbations from passing stars nudge an Oort Cloud object inward, it becomes a long-period comet, plunging toward the inner solar system on its first visit in eons. Comets like Hale-Bopp, which dazzled observers in 1997, and Comet McNaught in 2007, originate from the Oort Cloud. These dirty snowballs, kilometers across, grow tails millions of kilometers long as the Sun's heat vaporizes their ices. Studying comets gives us glimpses into the solar system's birth. They contain pristine water, organic molecules, and minerals unchanged since our system formed. The European Space Agency's Rosetta mission, which orbited Comet 67P from 2014 to 2016, analyzed a Kuiper Belt comet, revealing complex organic molecules and suggesting comets might have delivered the building blocks of life to Earth. So where does our solar system actually end? The answer depends on how you define it. If you mean the Sun's gravitational dominance, the edge lies where the Sun's gravity equals that of nearby stars, somewhere in the Oort Cloud, perhaps 50,000 to 100,000 AU away. If you mean the boundary of the Heliosphere, the bubble of charged particles blown by the solar wind, that's much closer at about 100 to 120 AU. The Voyager spacecraft have crossed into interstellar space, though they're still technically within the solar system's gravitational influence. Voyager 1 crossed the Heliopause, the boundary where the solar wind meets the interstellar medium, in 2012 at about 122 AU, or about 18 billion kilometers from the Sun. Voyager 2 followed in 2018 at about 119 AU. These spacecraft, launched in 1977, have traveled for over 45 years and are now more than 22 light-hours away, so far that radio signals take more than 22 hours to reach them and another 22 hours to return. Let's put this in perspective with a scale model. If Earth were the size of a peppercorn, about 2 millimeters across, the Moon would be a pinhead about 6 centimeters away. The Sun would be a sphere 22 centimeters in diameter, about the size of a large grapefruit, located 15 meters away from our peppercorn Earth. Mercury would be a grain of sand 5.8 meters from the grapefruit Sun. Venus would be another peppercorn at 11.4 meters. Mars would sit at 23 meters, and the asteroid belt would span from 33 to 48 meters. Jupiter, the largest planet, would be a small orange, about 2.2 centimeters across, sitting 116 meters from the Sun, farther than a football field. Saturn would be at 213 meters, over 2 football fields away. Uranus would be at 430 meters, nearly half a kilometer. Neptune would sit at 673 meters. Pluto would be another grain of sand at about 900 meters, nearly a kilometer from our grapefruit Sun. But the Oort Cloud in this scale, it would extend 30,000 kilometers, almost the entire diameter of the real Earth. The nearest star, Proxima Centauri, would be about 4,000 kilometers away, roughly the distance from New York to London. This scale model reveals the profound emptiness of space. Our solar system is mostly nothing, with tiny specks of matter separated by enormous voids. The Heliosphere, the Sun's magnetic influence stretching to about 120 AU, forms a protective bubble shielding the planets from galactic cosmic rays, high-energy particles from supernovae and other violent cosmic events. Without this protection, radiation levels would be much higher, potentially hindering the development of life on Earth. The Voyager spacecraft, now in interstellar space, report that cosmic ray intensity increased significantly once they crossed the Heliopause, confirming that the Heliosphere acts as a shield. The Interstellar Boundary Explorer, or IBEX, launched in 2008, maps the Heliosphere's edge from Earth orbit by detecting energetic neutral atoms created where the solar wind collides with the interstellar medium. These observations revealed that the heliosphere isn't spherical but elongated, with a long tail extending downwind from our Sun's motion through the galaxy. The shape reminds astronomers of a comet. Our entire solar system is, in a sense, a comet traveling through the galaxy at about 230 kilometers per second. This motion through space adds another dimension to understanding our solar system's size. We're not stationary. We're hurtling through the Milky Way galaxy, orbiting the galactic center once every 225 to 250 million years. This galactic year means that when dinosaurs first appeared, our solar system was on the opposite side of the galaxy. Since Earth formed 4.5 billion years ago, we've completed about 20 galactic orbits. Our solar system is like a ship sailing through an ocean of stars, and the heliosphere is our ship's bow wave. The Sun's gravity extends far beyond the heliosphere. An object orbiting at 50,000 AU would still be gravitationally bound to the Sun, though its orbital period would be millions of years. At these distances, the gravitational pull of passing stars becomes significant. The closest stellar approach we know of in recent history was Schultz's star, a red dwarf that passed within 0.8 light-years, about 50,000 AU 70,000 years ago, potentially disturbing Oort Cloud objects and sending some hurtling toward the inner solar system as comets we might see millennia from now. Planet 9, a hypothetical planet proposed to explain unusual orbital clustering of certain distant Kuiper Belt objects, might orbit at 300 to 1,000 AU with an orbital period of 10,000 to 20,000 years. If it exists, and the evidence is intriguing but not conclusive, it would be a super-Earth, perhaps 5 to 10 times Earth's mass, lurking in the outer darkness. Several survey projects are searching for this potential world, including the Vera Rubin Observatory, set to begin operations in the mid-2020s. The search for Planet 9 illustrates how much we still don't know about our own solar system. We've mapped distant galaxies billions of light-years away, yet a substantial planet might be hiding in our cosmic backyard, too faint and slow-moving to have been detected yet. This reminds us that exploration isn't finished. Mysteries remain even in our local neighborhood. Every generation discovers something that previous astronomers missed. Let's discuss the distances our spacecraft have achieved. As of 2024, Voyager 1 is about 160 AU from the Sun, roughly 24 billion kilometers. It's traveling at about 17 kilometers per second relative to the Sun. At this speed, it would take about 73,000 years to reach Proxima Centauri if it were headed that direction, which it isn't. Voyager 1 is heading toward the constellation Ophiuchus and will pass within 1.6 light-years of the star Gliese 445 in about 40,000 years. New Horizons, having visited Pluto and Arrokoth, continues outward at about 14 kilometers per second. It's currently about 55 AU from the Sun and will eventually enter interstellar space like the Voyagers, though its power supply will likely fail before it crosses the Heliopause. Pioneer 10 and 11, launched in the early 1970s, are also heading into interstellar space, though we lost contact with them decades ago. They drift silently outward, carrying plaques showing humanity's appearance and our solar system's location, messages in bottles for any civilization that might find them in the far future. These spacecraft represent the farthest humanity has physically reached, and the distances they've covered are humbling. Despite traveling for decades at speeds that would circle Earth in under 2.5 hours, they've barely left the front yard. The sheer scale of the solar system dwarfs our fastest machines. Even our most powerful rockets, operating continuously, would take centuries to reach the Oort Cloud. The power requirements for communicating with these distant probes are staggering. Voyager's transmitters broadcast with only 23 watts, about as much as a refrigerator light bulb. By the time those signals reach Earth from 160 AU away, they've spread out so much that NASA's Deep Space Network antennas receive only about 10 to the negative 18 watts, a quintillionth of a watt. It's like detecting a whisper from halfway across the United States. The fact that we can still communicate with Voyager after 45 years is a triumph of engineering. The Deep Space Network, with antenna complexes in California, Spain, and Australia, forms humanity's lifeline to the outer solar system. These giant dishes, up to 70 meters in diameter, track spacecraft across billions of kilometers. As spacecraft venture farther, communication becomes slower and more difficult. Data rates from New Horizons at Pluto were just 1 kilobit per second. It took over a year to download all the data from its Pluto encounter. Patience becomes essential when exploring the outer solar system. The inverse square law governs how quickly signals weaken with distance. Double the distance, and the signal strength decreases to 1/4. At Pluto's distance, signals are about 900 times weaker than from Mars. At the Oort Cloud, thousands of times farther still, communication would require enormous dishes or transmitter powers far beyond current spacecraft capabilities. This fundamental physics constraint means that exploring the outer reaches of our solar system presents challenges beyond just travel time. Future missions might use nuclear electric propulsion or solar sails to reach greater speeds. The Parker Solar Probe, studying the Sun's corona, achieved speeds of 192 kilometers per second using gravity assists from Venus, the fastest human-made object ever. However, it achieved this speed diving toward the Sun, not away from it. Reaching such velocities while heading outward remains beyond current technology. Even at those record speeds, reaching the Oort Cloud would take thousands of years. The Breakthrough Starshot initiative proposes using ground-based lasers to push lightweight Starship spacecraft to 20% of light speed, reaching the nearest stars in decades rather than millennia. If such technology works, we could send tiny probes through the Oort Cloud in months or years instead of centuries. These chips would capture images and data while zooming past at 60,000 kilometers per second, too fast to stop or orbit, but fast enough to explore distant regions within a human lifetime. Understanding our solar system's true size changes how we think about space exploration. Science fiction often depicts spacecraft hopping between planets like cars, driving between cities. The reality is vastly more challenging. Even with nuclear rockets or ion drives, trips to the outer planets take years or decades. The distances involved make space exploration a multi-generational endeavor. The engineers who designed Voyager have retired or passed away, yet their spacecraft continue functioning, maintained by new generations of mission controllers. This multi-generational aspect connects us to the deep time of astronomy. When Galileo first observed Jupiter's moons in 1610, he couldn't have imagined spacecraft orbiting them. When astronomers discovered Neptune in 1846 through mathematical predictions of its gravitational influence on Uranus, they couldn't have conceived of Voyager 2 visiting 143 years later. The work we do now exploring the solar system builds on centuries of accumulated knowledge and prepares the foundation for discoveries our great-grandchildren will make. Let's consider the solar system's mass distribution, because it illuminates why distances matter so much. The Sun contains 99.86% of the solar system's mass. Jupiter contains about 70% of the remaining mass. Everything else, 7 other planets, hundreds of moons, millions of asteroids, billions of comets, and all the dust and gas between, accounts for less than 0.2% of the total. We live in a solar system dominated by a single star, with a giant planet as a distant second and everything else as mere footnotes. This mass distribution determines the orbital dynamics that govern travel through the solar system. Moving between planets isn't like driving between cities on a flat road. You're navigating a complex gravitational landscape where the Sun's overwhelming pull must be balanced against planetary gravitational assists, orbital mechanics, and the tyranny of the rocket equation, which says that carrying more fuel requires more fuel to lift that fuel in an escalating spiral of diminishing returns. The Hohmann transfer orbit, the most fuel-efficient path between two planets, takes advantage of orbital mechanics to minimize energy requirements. To reach Mars, spacecraft don't aim at where Mars is, but where it will be 6 to 9 months later when the spacecraft arrives. The launch window timing is critical. Miss it, and you wait another 26 months for the planets to align favorably again. For outer planets, these calculations become more complex, often requiring gravity assists from multiple planets to gain speed without burning excessive fuel. Gravity assists, or gravitational slingshots, let spacecraft steal momentum from planets. Voyager 2 visited all 4 giant planets by carefully threading a path that used each planet's gravity to boost its speed and bend its trajectory toward the next target. This cosmic billiards requires precise timing and navigation. The planets must align in a particular configuration, which for all 4 giants happens only once every 176 years. Voyager launched during this rare alignment, and we won't see another until the 22nd century. The challenges of distance also affect our understanding of what exists in the outer solar system. We've observed only a tiny fraction of Kuiper Belt objects. Most are too small and distant to detect with current telescopes. Estimates suggest there might be 100,000 objects larger than 100 kilometers in the Kuiper Belt, and perhaps trillions of smaller bodies. Each is a world unto itself with its own history, composition, and story. We've seen fewer than 10 up close. The scattered disk and Oort Cloud remain largely theoretical constructs based on orbital calculations and comet origins. We can't see individual Oort Cloud objects. They're too small and too far away, reflecting too little sunlight for even our best telescopes to detect. We infer the Oort Cloud's existence from the trajectories of long-period comets, which suggest they originate from a vast reservoir of icy bodies surrounding the solar system. The cloud might contain more comets than there are stars in the galaxy, yet we can't directly observe a single one until it's disturbed and begins falling sunward. This vast frontier of unexplored territory reminds us that we're still in the early stages of understanding our cosmic neighborhood. The next generation of telescopes, like the Vera-Rubin Observatory, with its 8.4-meter mirror and massive camera capable of imaging the entire visible sky every few nights, will discover thousands of new Kuiper Belt objects and potentially detect Planet 9 if it exists. These discoveries will refine our understanding of the solar system's outer boundaries and perhaps reveal surprising structures we haven't anticipated. The James Webb Space Telescope, operational since 2022, can observe the outer solar system with unprecedented sensitivity. While designed primarily to study distant galaxies and exoplanets, Webb's infrared capabilities let it detect the faint heat signatures of distant solar system objects. It has already observed Neptune's rings in detail not seen since Voyager 2's flyby, and will continue studying Kuiper Belt objects, potentially revealing their surface compositions and atmospheres. Size comparisons with other planetary systems put our solar system in context. We've discovered over 5,000 exoplanetary systems, and they display remarkable diversity. Some systems pack multiple planets closer to their star than Mercury is to our Sun. Others have giant planets in tight orbits, completing a year in days. Some stars have planetary systems extending beyond 100 AU, while others seem to have planets only in their inner regions. Our solar system, with its particular architecture, small rocky planets inside, giant planets outside, and a vast debris field beyond, represents just one possible configuration among many. The NICE model, named after the French city where it was developed, describes how our solar system evolved to its current configuration. It proposes that the giant planets formed closer together and to the Sun than their current positions. Gravitational interactions between planets and the disk of planetesimals caused the giants to migrate outward, with Jupiter moving slightly inward, while Saturn, Uranus, and Neptune moved substantially outward. This migration scattered planetesimals into the Kuiper Belt and Oort Cloud, explaining why those regions contain debris from the inner solar system. The late heavy bombardment, approximately 600 million years after the solar system's formation, might have resulted from this planetary migration. As the giants moved, their gravitational influence destabilized asteroid and comet orbits, sending billions of objects careening through the inner solar system. The Moon's heavily cratered surface preserves evidence of this intense period of impacts. Earth experienced similar bombardment, though plate tectonics and erosion have erased most traces. This violent reshuffling fundamentally changed the solar system's structure, expanding it and distributing material across vast distances. Understanding these migration processes helps explain the solar system's current size. The planets we see didn't form where they are now. They moved, pushing and pulling on countless smaller bodies, flinging some into distant orbits and ejecting others from the solar system entirely. Rogue planets wandering through interstellar space, unattached to any star, might be ejection survivors from systems like ours. Our solar system might have ejected several ice giants during its chaotic youth, and we might have captured objects that originated around other stars. The possibility of interstellar objects passing through our solar system became concrete with Oumuamua's discovery in 2017. This elongated object, tumbling through space at 26 kilometers per second, came from another star system, the first confirmed interstellar visitor. Its trajectory, speed, and origin outside our solar system proved that objects travel between stars. Oumuamua spent only a few months in the inner solar system before departing, never to return. In 2019, Comet Borisov became the second confirmed interstellar visitor, this one clearly a comet from its appearance and behavior. These interstellar travelers suggest that the boundary between our solar system and interstellar space is more permeable than we imagined. Objects drift in and out, exchange between stellar systems over millions of years. The Oort Cloud might contain objects captured from other stars during close encounters in our Sun's youth, when it was part of a star cluster before drifting into its current isolation. Some Oort Cloud comets might have formed around other stars entirely, making them interstellar immigrants that settled permanently in our system. The Sun's position within the galaxy influences our solar system's size and structure. We orbit in a relatively calm region of the Milky Way between spiral arms, where stellar encounters are rare. The nearest star, Proxima Centauri, is 4.24 light-years away, about 268,000 AU. In denser regions of the galaxy, stars might be separated by only hundreds of AU, and gravitational interactions would continually strip away outer Oort Cloud objects, preventing distant reservoirs like ours from existing. Our location in a sparse neighborhood allows our solar system to extend so far without disruption. Every 250,000 years or so, a star passes within about 1 light-year of our Sun, potentially disturbing the Oort Cloud and sending comets toward the inner system. These encounters don't destroy the solar system, but they stir it, creating comet showers that last for millions of years. The dinosaurs' extinction 66 million years ago resulted from an asteroid impact, but some mass extinction events in Earth's history might correlate with comet bombardment triggered by stellar encounters. The outer reaches of our solar system couple us to galactic dynamics, making us subject to influences from passing stars. Our motion through space also subjects the solar system to varying radiation environments and interstellar medium densities. The local interstellar cloud, a region of slightly denser hydrogen we're currently passing through, affects the heliosphere's size and shape. Over tens of thousands of years, as the Sun moves through different regions of interstellar space, the heliosphere expands and contracts, sometimes extending to 150 AU, other times compressing to 80 AU. This breathing motion influences cosmic ray exposure for the planets, potentially affecting atmospheric chemistry and climate over very long timescales. The solar wind, a continuous stream of charged particles from the Sun's corona, fills the heliosphere with about 5 particles per cubic centimeter near Earth, far better than any vacuum we can create in laboratories, yet enough to affect spacecraft electronics and contribute to atmospheric loss on planets without strong magnetic fields. Mars, lacking a global magnetic field, slowly loses its atmosphere to the solar wind, a process that has thinned its atmosphere over billions of years. Understanding the heliosphere's extent helps us understand planetary habitability and how stellar environments affect planetary atmospheres. The zodiacal light, a faint glow visible from dark locations before dawn or after sunset, comes from sunlight reflecting off dust particles throughout the inner solar system. This dust, debris from asteroid collisions and cometary shedding, forms a disk extending from the Sun's immediate vicinity to the asteroid belt and beyond. The Juno mission detected dust particles at Jupiter, and even in the outer solar system, tiny grains persist, remnants of collisions and cometary outgassing over billions of years. Our solar system isn't empty, it's filled with invisible dust, gas, and charged particles, creating a complex environment spacecraft must navigate. Radiation belts, regions where planetary magnetic fields trap charged particles, present hazards for spacecraft. Earth's Van Allen belts, discovered by the Explorer missions in 1958, contain protons and electrons at energies that can damage electronics and endanger astronauts. Jupiter's radiation belts are thousands of times more intense than Earth's, powerful enough that the Juno spacecraft required special shielding, and its orbit was carefully designed to minimize radiation exposure. These radiation environments extend far from planets, creating invisible danger zones that affect mission planning. The concept of the Heliosphere defines the region around each planet where its gravity dominates over the Sun's. Earth's Heliosphere extends about 1.5 million kilometers, roughly 4 times the Moon's distance. Jupiter's Heliosphere is enormous, extending 53 million kilometers, which is why it can hold dozens of moons in stable orbits. Beyond a planet's Heliosphere, objects are more strongly attracted to the Sun than the planet, setting practical limits on how far planetary moons can orbit. This gravitational architecture creates nested zones of influence throughout the solar system. Trojan asteroids share orbits with planets held in stable Lagrange points 60 degrees ahead of or behind the planet. Jupiter has over 9,000 known Trojans, while Neptune, Mars, Earth, and Uranus also have Trojan companions. These objects occupy gravitational balance points where the planet's and Sun's gravity combine to create stability. The James Webb Space Telescope discovered that even Neptune's moon Triton has a thin atmosphere, demonstrating that active processes continue throughout the solar system, even in regions we considered geologically dead. Lucy, a NASA mission launched in 2021, is visiting Jupiter's Trojan asteroids, regions never before explored by spacecraft. These primitive bodies, preserved in cold storage for billions of years, offer insights into the solar system's formation. Lucy will visit 8 asteroids over 12 years, executing a complex trajectory involving gravity assists from Earth and traveling distances exceeding 6 billion kilometers. The mission exemplifies how exploring our solar system requires patience, precision, and a willingness to commit decades to a single journey. Psyche, another NASA mission launched in 2023, is heading to a metal-rich asteroid between Mars and Jupiter. Scientists suspect 16 Psyche might be the exposed core of a protoplanet whose rocky exterior was stripped away by ancient collisions. If true, visiting Psyche offers a rare glimpse into planetary interiors, allowing us to study the iron-nickel core of a differentiated world without drilling through thousands of kilometers of rock. The mission highlights how diverse even the asteroid belt is, not just rocky debris, but remnants of failed planets, each with unique histories. The concept of living space in the solar system, regions where liquid water might exist, has expanded dramatically. We once thought only Earth's surface could harbor liquid water. Now we know that several moons, Europa, Enceladus, Titan, possibly Ganymede, Callisto, and others, likely harbor subsurface oceans containing more water than all of Earth's oceans combined. These hidden seas, kept liquid by tidal heating from gravitational interactions with their parent planets, might harbor life evolved independently from Earth. The solar system's habitable zone isn't just a narrow ring around the Sun, but includes moons throughout the outer system. Enceladus, a small moon of Saturn only 500 kilometers across, erupts plumes of water from its south polar region, spraying ocean material into space. The Cassini spacecraft flew through these plumes, detecting water, organic compounds, and salts indicating a salty ocean beneath the ice, an ocean in contact with a rocky sea floor where chemical reactions could provide energy for life. Enceladus reminds us that habitability doesn't require Earth-like conditions. liquid water, energy sources, and organic chemistry might be enough, and these exist throughout our solar system. The search for life beyond Earth is no longer limited to Mars. Missions are being planned to Europa, Enceladus, and Titan. The Europa Clipper, scheduled to launch in 2024, will make dozens of flybys to study Europa's ice shell and ocean. The Dragonfly mission, launching in 2027, will send a rotorcraft to explore Titan, flying between landing sites to study its methane lakes, organic chemistry, and potential prebiotic chemistry. These missions represent a shift in astrobiology. Life might be common in the solar system, just not on surfaces but hidden beneath ice, protected from radiation and extreme conditions. The distances involved make these missions extraordinarily challenging. Europa Clipper will take 5.5 years to reach Jupiter, executing gravity assists from Mars and Earth. Dragonfly will take 7 years to reach Titan. Sample return missions, which would collect material from these worlds and bring it back to Earth for detailed analysis, would require even longer timelines, possibly 15 to 20 years round trip. Yet these missions are worth the investment because discovering life elsewhere in our solar system would answer one of humanity's most profound questions. Are we alone? The deep time required for solar system exploration forces us to think across generations. Children born when Juno launched in 2011 are now teenagers watching its discoveries at Jupiter. Babies born when New Horizons launched in 2006 were in elementary school when it reached Pluto. The Voyager spacecraft, launched before many current mission scientists were born, continued transmitting data that those scientists analyze. This multi-generational arc of exploration creates continuity, connecting past, present, and future in a shared human endeavor. The economic value of understanding our solar system's size extends beyond pure science. Asteroid mining proposals target near-Earth asteroids for resources, water, platinum group metals, and other valuable materials. The distances to these asteroids range from millions to hundreds of millions of kilometers, making round-trip missions feasible within years rather than decades. Water extracted from asteroids could fuel spacecraft, provide life support for astronauts, and eliminate the need to launch these heavy resources from Earth's deep gravity well. Understanding orbital mechanics and distances determines whether these ventures are practical or fantasy. Mars colonization proposals must grapple with the planet's distance. Communication delays of 4 to 24 minutes mean colonists couldn't call home for help. They'd need to solve problems independently. Supply missions from Earth would take 6 to 9 months, requiring colonies to be largely self-sufficient. The psychological impact of being 100 to 400 million kilometers from Earth, knowing rescue is impossible if something goes wrong, would profoundly affect colonists. Distance creates both physical and psychological isolation. The Mars Society's Mars Desert Research Station and other analog facilities on Earth simulate the isolation and communication delays of Mars missions. Participants experience the frustration of working under time-delayed communication, making the abstract distances tangible. These simulations reveal that distance affects not just logistics, but psychology, decision-making, and social dynamics. Understanding our solar system's scale isn't just about kilometers, it's about time delays, isolation, and the human factors that come with being millions of kilometers from home. Terraforming Mars, transforming it into an Earth-like world, would require resources and timescales that dwarf any project humanity has attempted. Estimates suggest it might take centuries to millennia to warm Mars, thicken its atmosphere, and establish ecosystems that could support human life without spacesuits. The distances involved mean that Mars colonization wouldn't be a short-term project, but a civilizational commitment spanning generations. Children born on Mars would experience Earth only through stories and transmissions delayed by light speed limitations. The Fermi paradox, The question of why we haven't detected alien civilizations, despite the vast number of stars in the galaxy, takes on new dimensions when considering our solar system's scale. If interstellar travel is difficult, perhaps aliens remain in their solar systems, never venturing to the stars. The distances we've discussed within our solar system are tiny compared to interstellar space. Proxima Centauri is 63,000 times farther than Pluto. If our solar system's distances challenge us, interstellar distances might be insurmountable barriers that keep civilizations isolated. Yet our expanding understanding of exoplanets reveals thousands of solar systems with different architectures. Some have hot Jupiters, gas giants orbiting closer to their stars than Mercury orbits our Sun. Others have super-Earths in tight orbits or planetary systems packed into spaces smaller than Mercury's orbit. Each configuration presents different challenges for exploration and different opportunities for life. Our solar system, with its specific arrangement and scale, is just one example among countless possibilities. The concept of a Dyson sphere, a hypothetical megastructure encompassing a star to capture all its energy, illustrates how advanced civilizations might eventually utilize their solar system's entire volume. At 1 AU from the Sun, a Dyson sphere would have a surface area about 500 million times Earth's surface. At Jupiter's distance, the surface area would increase proportionally with the square of the radius, becoming billions of times larger. The sheer scale of our solar system means that even a civilization capable of such megastructures would have vast spaces to work with. Our Sun will eventually exhaust its hydrogen fuel in about 5 billion years, expanding into a red giant that will likely engulf Mercury, Venus, and possibly Earth. The habitable zone will shift outward, potentially warming the moons of Jupiter and Saturn to temperatures where liquid water could exist on their surfaces. This far future evolution reminds us that the solar system isn't static, it evolves, and its habitability changes over time. Understanding its current size helps us model its past and future states. When the Sun becomes a red giant, its expanded atmosphere might extend to Earth's current orbit or beyond, dramatically changing the inner solar system. The outer planets will survive, though their surfaces and atmospheres will warm. Titan might become temperate. Europa's ice shell could melt, revealing its ocean to open space. These transformations, billions of years in the future, demonstrate that what we consider the solar system's size and structure are temporary states in a dynamic, evolving system. Eventually, the Sun will shed its outer layers, creating a planetary nebula, a glowing shell of gas expanding into space. The Sun's core will collapse into a white dwarf about Earth-sized, but containing roughly half the Sun's current mass. The surviving planets will orbit this stellar remnant in darkness, their surfaces frozen at temperatures approaching absolute zero. The solar system will continue to exist, but transformed beyond recognition, its scale maintained even as its energy source fades. Over trillions of years, gravitational interactions will slowly disrupt planetary orbits. Some planets might be ejected into interstellar space, while others could spiral into the white dwarf remnant. The solar system will gradually dissolve, its planets scattered, its structure erased by time and chaos. Yet even in this far future, the fundamental distances, the AUs between orbital shells, the vast expanses of the Oort Cloud, will persist until the last bound objects finally drift away. The scale we've discussed represents not just current reality, but a legacy that will outlast the Sun itself. The study of our solar system's size connects to fundamental physics. The spacing of planetary orbits follows patterns that aren't fully understood. Bode's law, formulated in the 18th century, provided a mathematical formula that roughly predicted planetary distances, though it broke down for Neptune. Why planets settled into particular orbits during formation remains an active area of research. The The distances between planets aren't random but result from complex gravitational interactions during the solar nebula's collapse and the subsequent migration of forming planets. Resonances between planets, where orbital periods form simple ratios, stabilize or destabilize orbits over millions of years. Neptune and Pluto are in a 3-to-2 resonance. For every 2 orbits Neptune completes, Pluto completes 3. This resonance prevents them from ever colliding despite their orbits crossing when viewed from above. Jupiter's moons, Io, Europa, and Ganymede, are locked in a 4-to-2-to-1 resonance, creating tidal heating that powers Io's volcanoes and likely maintains Europa's ocean. These resonances shape the solar system's architecture on scales from thousands to billions of kilometers. The NICE model and other formation theories attempt to explain why our solar system has its particular size and structure. Computer simulations, starting with a disk of gas and dust around the young sun, can reproduce solar systems with various architectures depending on initial conditions and the timing of key events. Some simulations produce systems like ours, while others generate very different configurations. The fact that we can model these processes suggests we understand the fundamental physics, even if predicting specific outcomes remains challenging. One profound realization from studying our solar system scale is how empty space truly is. The average density of matter in the solar system, if you averaged everything, sun, planets, asteroids, dust, and gas, across the entire volume out to the Oort Cloud, would be extraordinarily low. You could fit all the planet's mass into a sphere smaller than the Moon, yet this matter is distributed across a region trillions of kilometers across. We live in a universe where matter is the exception and emptiness the rule. This emptiness has philosophical implications. The vast distances between worlds ensure that life on Earth evolved in isolation, unaffected by biological processes elsewhere in the solar system. If life exists on Europa or Enceladus, it evolved independently, representing a separate genesis. The distances protected these potential biospheres from contamination, allowing multiple experiments in life's origins to proceed simultaneously but separately. When we finally explore these worlds, we must be careful not to contaminate them with Earth life, preserving the scientific value of studying independent examples of biology. The Outer Space Treaty of 1967 and subsequent agreements on planetary protection established protocols to prevent contamination. Spacecraft visiting potentially habitable worlds must be sterilized to extremely high standards, reducing the chance of transporting Earth microbes. The distances involved actually help with this. The harsh radiation environment of space, the vacuum, and the extreme temperatures kill most organisms during the years-long journeys. Yet hardy microbes can survive, making contamination prevention essential for responsible exploration. The James Webb Space Telescope's ability to detect biosignatures in exoplanet atmospheres from thousands of light-years away contrasts starkly with our difficulty exploring our own solar system's potentially habitable worlds. We can study distant exoplanets' atmospheric chemistry using transit spectroscopy, but to truly understand Europa's ocean or Enceladus's plumes requires sending spacecraft there, journeys taking years and costing billions. The irony is that some questions about distant systems are easier to answer than questions about our cosmic backyard. Understanding our solar system's true scale instills humility. We've walked on one world beyond Earth, the Moon, just 1.3 light-seconds away. We've soft-landed robots on 4 others, Venus, Mars, Titan, and asteroids Ryugu and Bennu. We've orbited 8 bodies beyond Earth, the Moon, Mars, Venus, Jupiter, Saturn, Vesta, Ceres, and comets. Out of hundreds of thousands of solar system objects larger than a kilometer, we've closely examined fewer than 100. We've barely begun exploration of our cosmic neighborhood, yet every mission expands our understanding. The Rosetta mission's study of Comet 67P revealed that its water had different isotopic ratios than Earth's oceans, suggesting comets might not have delivered all our water. The Dawn mission's observations of Ceres found ammonia-bearing minerals, suggesting materials from the outer solar system mixed into the asteroid belt. New Horizons showed that Pluto is geologically active despite being billions of kilometers from the Sun, challenging assumptions about what powers planetary processes. Each discovery reveals that our solar system is more complex, more dynamic, and more surprising than we expected. The future of solar system exploration includes missions we can barely imagine. Solar sails pushed by lasers, nuclear electric propulsion, or fusion drives might enable faster travel to the outer planets. Miniaturized spacecraft could be deployed by the hundreds, creating swarms that explore multiple targets simultaneously. Artificial intelligence might enable spacecraft to make autonomous decisions, adapting to discoveries without waiting hours for instructions from Earth. These technologies could transform our exploration capabilities, making the solar system's vast distances less of a barrier. The possibility of human expansion throughout the solar system, bases on the Moon and Mars, mining operations on asteroids, research stations orbiting Jupiter's moons, seems like science fiction. Yet every step is technically feasible with sufficient investment and commitment. The distances and timescales require patience and resources that test our civilization's ability to plan beyond quarterly earnings reports and election cycles. Whether we choose to become a multi-world species depends not on technology, but on whether we collectively decide it's worth the effort. Some argue that space exploration is a luxury we can't afford, while problems persist on Earth. Others counter that the technologies developed for space exploration, water purification, renewable energy, closed-loop life support, materials science, directly benefit life on Earth. The satellite infrastructure we take for granted, communications, GPS, weather forecasting, Earth observation, exists because we've ventured into space. Understanding our solar system's resources, water on the Moon, metals in asteroids, fusion fuel in the gas giants, might provide solutions to resource scarcity on Earth. The psychological value of exploration extends beyond practical benefits. Knowing the true scale of our solar system, understanding our place within it, connects us to something larger than our individual lives. The images from Voyager, Cassini, New Horizons, and other missions inspire wonder, reminding us that we're part of a universe vast beyond comprehension yet understandable through science. This inspiration drives young people into STEM careers, fuels curiosity, and enriches human culture with knowledge and perspective. Every atom in your body except hydrogen was forged in the cores of massive stars that exploded billions of years ago, scattering their enriched material into space. That material eventually collapsed into the solar nebula that formed our Sun and solar system. You are literally made of stardust, assembled from atoms that have traveled through space and time to become you. Understanding our solar system's scale means understanding the distances those atoms traveled, the cosmic processes that created them, and the improbable journey that led to your existence. The solar system's size provides perspective on our cosmic significance. Earth is tiny, a pale blue dot, as Carl Sagan described it, suspended in a sunbeam. Yet on this dot, every human who ever lived experienced all their triumphs and tragedies. All of history happened within a few kilometers of this planet's surface. We're infinitesimally small compared to the solar system, which is itself infinitesimally small compared to the galaxy, which is tiny compared to the observable universe. This perspective can be humbling or empowering. We're insignificant on cosmic scales, yet we're the universe's way of understanding itself. As we conclude this journey through our solar system, remember that numbers alone, the AUs, the billions of kilometers, the light hours, don't capture the full reality. The solar system's size means that light from the Sun, which left 8 minutes ago, is only now reaching Earth. It means Voyager 1 signal transmitted hours ago is only now arriving at receiving dishes. It means that somewhere in the Oort Cloud, countless icy worlds orbit in darkness, completing journeys around the Sun that take millions of years, never to be seen by human eyes unless we someday venture there. The solar system is so large that our fastest spacecraft take decades to traverse it. So large that comets from its outer reaches take millions of years to fall sunward. So large that the Sun's gravity remains dominant 1 light-year away, far beyond anything we've explored. Yet it's also small, a bubble of warmth and light in the vast darkness between stars, a fragile collection of worlds bound by gravity to a single star in a galaxy of hundreds of billions. Our solar system is our cosmic home, the only environment in the universe we know with certainty harbors life. Every living thing on Earth exists because this solar system has the right size and structure, massive Jupiter protecting the inner planets from excessive comet impacts, Earth at just the right distance from the Sun for liquid water, the Asteroid Belt providing raw materials for planet formation without coalescing into another planet that might have destabilized Earth's orbit. The scale of our solar system isn't just a fact, it's a prerequisite for our existence. As telescopes improve and missions venture farther, our understanding of the solar system's size and structure will continue to evolve. We'll discover new dwarf planets in the Kuiper Belt, better characterize the Oort Cloud, and perhaps find the hypothetical Planet 9. We'll send more sophisticated robots to explore the outer moons, and perhaps eventually humans will follow. The solar system we know today is just the beginning of the solar system we'll understand tomorrow. Thank you for joining me on this journey from Earth to the very edges of our solar system. I hope you now appreciate the staggering distances that define our cosmic neighborhood and feel a deeper connection to the Sun, planets, moons, asteroids, and comets that share our small corner of the galaxy. The next time you look at the Moon, remember that it's just the first step in a journey spanning billions of kilometers. The next time you see Jupiter shining in the night sky, remember that it's over 700 million kilometers away, and beyond it lie worlds even more distant and mysterious. Keep looking up at the stars, keep asking questions about the universe, and never forget that you're part of something vast and magnificent. You're made of atoms from exploded stars, standing on a planet, orbiting a sun in a solar system billions of kilometers across, all of it part of a galaxy containing hundreds of billions of stars. You're not just in the universe, you are the universe, experiencing itself, asking questions about its own nature and scale. Until next time, may your curiosity guide you toward ever deeper wonder at the cosmos we call home. If you made it through this entire cosmic reality check, you're exactly who I make these videos for. Subscribe for more mind-expanding journeys through space and time, and please give a thumbs up. And if you enjoyed this video, I am sure you will love this other one at the left side of the screen. How big is the universe compared to the Milky Way? In this video, we break down the true scale of the universe, the mysteries of dark matter and dark energy, and why our galaxy is just a tiny bubble in a possibly infinite cosmos. See you there.